Hello, greetings to everyone. I am Adarsh. I will be presenting our paper titled Anomaly in Respiratory Sinus Arrhythmia, Multiple Heart Rate Variability Cycles Within Each Breathing Cycle at Low Breath Rates with Breath Holds. Introduction. The primary inputs of energy to the human body are the air that we breathe and the food that we consume. The respiratory system is a complex system intricately connected to a large number of physiological phenomena in the body, out of which many of these interactions are yet to be completely understood. The ancient texts on yoga, such as the Tirumantiram of Tirumular, the Dikshavidi of Agastya, the Yoga Shastra of Patanjali, have laid a lot of emphasis on these controlled breathing practices, known generally as pranayama. These practices have been known to have a positive impact on the human health and wellness. But most of the research on yoga, pranayama, and meditation deal with the after effects of these practices and rarely on the physiological mechanisms behind these practices. This kindled our interest to study what aspects of our physiology gets affected during these breathing practices. The study design. 10 healthy subjects were chosen who had no prior exposure to yoga or pranayama. The subjects sat in an upright relaxed posture and were asked to pace their breathing in synchronous to a metronome. The metronome was programmed to generate 8 different rates from 60 to 2 cycles per minute. The ECG and respiration were recorded using the Ant Neuro Ego MyLab system at a sampling rate of 512 Hz. Baseline was recorded before and after the task. The subjects were asked to breathe from 60 to 10 cycles per minute without holding their breath. The inhale and exhale durations were equal. The metronome here generated 2 distinct beeps. Then the subjects were asked to breathe from 5 to 2 cycles per minute with breath hold after every inhale and exhale. The inhale, exhale, and hold durations were all equal. Here, the metronome generated 4 distinct beeps. For every condition, we recorded for a duration of 2 minutes. The analysis. Here, we look for the relationship between the breathing phases and the increase and decrease in the heart rate, as well as the R wave amplitude with respect to the respiration. The respiration signal of each breathing rate is considered for obtaining the Fourier transform, the respiration rate, the inspiration and the expiration periods. The R waves were detected from the ECG signal using the threshold independent QRS detection algorithm based on the dynamic Poisson index. From the RR intervals, the instantaneous heart rate time series was obtained. The power spectra of the heart rate variability signal, the breathing signal, and the R to S amplitude time series were all obtained and compared. We also looked at the percentage change in the R to S amplitude relative to the baseline value for each respiration rate. The correlation between the R wave amplitude and the respiration signals were computed. Getting into the results. This figure shows the power spectrum of the respiration signal of a subject during the task. It is clearly seen that the metronome is able to help the subject breathe at a constant rate. The figure shows the variation of the ECG amplitude with the two phases of the respiration at a breathing rate of 2 cycles per minute. The blue trace is the respiration signal and the upward deflection corresponds to the inspiration. The R wave amplitude keeps decreasing during inspiration and increasing during expiration. This figure shows the extracted R wave amplitude time series plotted against the respiration signal. This figure shows the variation of the heart rate with the phases of the respiration for breathing rate of 2 cycles per minute. Unlike the well-known respiratory sinus arrhythmia, where the heart rate increases during inspiration and decreases during expiration, here we see 2 full cycles of peak-to-peak changes in the heart rate time series within each respiratory cycle. This anomaly has not been reported so far in the literature to the knowledge of the authors. It is especially interesting that the heart rate rises with the expiration during the second cycle of variation. This variation is completely against any understanding of the so-called phenomenon of the respiratory sinus arrhythmia. The plot of respiration, heart rate variability, and the R wave amplitude spectrum at low breathing rates of 532 cycles per minute are shown here. The second harmonics of the breathing frequency, namely at 0.1 and 0.066 Hz, are clearly visible in the heart rate variability spectrum for breathing rates of 3 and 2 cycles per minute. On the other hand, there are no such harmonics present in the R wave amplitude spectrum. This figure shows the spectral analysis of the respiration, heart rate variability, and the R wave amplitude. From the log spectral plots, we see that the spectrum of the RS amplitude signal closely follows that of the breathing spectrum, whereas the heart rate variability spectrum has a prominent second harmonic for the breathing rate of 5 cycles per minute, and both second and third harmonic for the breathing rate of 2 cycles per minute. This figure shows the error bar plots of the correlation coefficients between the normalized spectra of respiration and R wave amplitude and the heart respiration and the heart rate variability. The normalized spectra of respiration and R wave amplitude are highly correlated, with a correlation coefficient of above zero point 0.9 for low breathing rates of 5, 3, and 2 cycles per minute. On the other hand, the correlation coefficient between the heart rate variability and the breathing spectra ranges from 0.5 to 0.7 only for the same breathing rates of 5, 3, and 2 cycles per minute. Conclusion. At very low breathing rates, the R wave amplitude variations are completely in synchronization with the phases of the respiration, while the heart rate variations are not in synchronization with the phases of the respiration. It is observed that at very low breathing rates, the heart rate variations undergo 2 to 3 complete cycles within each respiratory cycle, which is unlike the respiratory sinus arrhythmia. Anomalous phenomenon of the heart rate variability is uniformly observed in all the subjects studied, even during the times when the breath is held after inhalation or exhalation. It is strictly not the same as what has been characterized as the respiratory sinus arrhythmia in the literature. It is likely that for reasons unknown at this time, the cardiac rate control centers at the medulla oblongata override the mechanism of the RSA at low breathing rates. The authors could not see any systematic study related to the respiratory modulation of the R wave amplitude in the literature during very slow breathing. Hence, this whole phenomenon requires a closer look by respiratory physiologists to explain the causative physiological mechanisms behind the anomalous variations in the heart rate. Thank you.